Process analysis with simulation. So in this lecture, we're going to extend our knowledge of process analysis by using software tools for simulation. So what is simulation modeling? Simulation modeling is the process of creating and using digital representations of real-world systems such as processes. And why do we want to do that? Why do we want to create a digital representation? Because we can play with it to understand the system. We can predict the performance of the system under various different conditions or loads or demand scenarios. We can test what-if scenarios. What happens if some workers are absent? What happens if there's a supply disruption? What happens if demand suddenly decreases or increases? We can do all these what-if scenarios. And so why do we want to do that? By building a digital model and doing a simulation, because it's risk-free, very low cost compared to the alternative of actually running a real experiment with a real company and doing real disruptions. And simulations are good because it's easy to capture complexity with them, which mirrors more closely what happens in real life, unlike spreadsheet models, which tend to get very difficult to handle if they get too complex. Also, in real life, there are uncertain things that you don't know for sure. So you want to model them using some sort of random process or random values. Spreadsheets are not really good at doing that. It improves decision making because you can stress test your process. You can do what-if scenarios. You can have plan B, plan C in place if something happens. You can evaluate improvements and see what the payback will be for different changes in the process. So that is why it's very, very useful. So we're going to use this free software called AnyLogic Personal Learning Edition, which you can download from the link given in the slides, or you can just search for AnyLogic Personal Learning Edition on Google, and the first or second link will take you there. And you can install it on Windows or Mac. And this is a very powerful industry strength software. If you get really good at it, just being very skilled with a software like this can be enough to land you a job in supply chain or operations, or even other areas, because you could build simulations like diffusion models, which look at how new inventions or innovations diffuse or gain market share. That could help you with marketing for a new invention. You could build models about how flu or COVID or diseases spread. You could do all sorts of things. And so I highly recommend that you will be doing a little bit of this software in this lecture to model some processes. But I highly recommend you continue your learning journey. You can find resources online. There's some YouTube videos. There's some webinars done by the company. They do trainings, which are not free though. You have to pay to get the training from them, and so on. So I highly recommend that this software, any other simulation software like it, is very, very useful. So what does it look like when you start the software and you do a new model? You come to a window like this, where on the left here, where it says palette, you have all of these libraries which come with, and this is the process modeling library selected. So each library has different blocks inside it, which implement some sort of logic. And so you can use these blocks to build simulations. So the process modeling library is where we are going to spend almost all of our time. Other key libraries are this agent library. We'll talk about agents in a second, in a moment. And the analysis library, which allows you to make plots, bar charts, or track statistics of different things happening. So you basically drag these blocks onto this area called main, and when you drop them, if you drop them close to another block, it automatically connects them, and you can see these connections. And then when you click on a block, it shows you the properties of the block on the right. And these are the properties that you're going to change to customize the block according to your needs. So we're going to talk about blocks in detail, but the source block, what it does is it injects units into your system. So it's used to model like customer arrivals. So maybe customer arrives into your system. Source block can be used to model demand. So there's demand for your products. It can be used to model arrivals of stuff from the supplier, any sort of thing entering your system. That's where your process starts. It has to work on something, right? Your process is going to work on products or some sort of raw material or customer. Your process has to work on something. So whatever thing your process works on, that thing is created in the source block and sent into your system. So your models will always start with a source block. Okay, and so you can define an arrival rate. So here I've defined an arrival rate of 10 per hour. So on average, 10 units, which could be products or customers or whatever, or patients in a healthcare setting, arrive per hour. The source block does do random arrivals using like a Poisson distribution, but the average rate will be 10. Okay. And then you can choose other blocks and change their properties. And then you press this green button to run the model and view the simulation results, the save button to save a model. And so it's pretty straightforward once you build a few models. The overall interface. Then obviously, learning all these libraries to build different types of models takes some learning and some time. Okay, so AnyLogic works when what it calls an agent-based paradigm. What does that mean? So agents are like the main building blocks in AnyLogic. An agent can be used to model product which is flowing through your system, or customers which are flowing through your system. Anything which flows through and can be inventoried or can be put in a queue or can be processed. We're going to model as agents. So in the picture, you have some examples of things that people model as agents. Could be people, people going through a process, going through an organization, going to an airport. Could be vehicles. Could even be non-material things as agents. So agent could be things like projects, innovations. Organizations could be agents if you are modeling different organizations and how they react to certain things. So depending on the simulation you're building, the thing that moves through your system and gets acted upon is the agent. You don't really have to think about it, because when you set up a simple simulation model, there's always a default agent that's going to go through your simulation. So the source block will generate these agents and put them into your system. So you don't have to think about it much for simple models, but for more advanced models, which we wouldn't get to in this lecture, but for more advanced models, you can have properties of agents. So for example, you can add variables to track certain things in agents. Let's say an agent is waiting. You may have a time tracking variable in an agent which tracks how long an agent had to wait, for example. You can have different types of agents. If you have two types of product that go through different parts of your process, you could do that. You could have a decision based on the agent type. If it's type A, that goes through this process, and if it's part of the process, and if it's type B, goes through another part of the process. So you could do all those sorts of things. So that's kind of like the agent is basically what's going to pass through your process and be acted upon. Let's understand some basic building blocks, and then let's get to building our simulation models. So the round block with a plus sign and an arrow going this way, this is called a source block. All these blocks have these green lights or circles. That means a connector. So if a block has one connector, it means it needs to be connected on this side to something else. If a block has two connectors, it needs to be connected on both sides to some other blocks. So the source block add agents to simulation over time based on a user-defined rate, like how many agents you want to put in per unit time. And that's basically based on the demand or the load on your process. So the more the demand or load, the higher the rate you would set. And the opposite of a source block is this at the bottom of the slide, which is an X in a circle called the sync block, which basically means the agent is done through your process. It's just leaving your shop or factory or your process. So they're done, they go out of the simulation. So sync block, as the name suggests, just syncs the agents, just takes them out of the simulation because they have been processed, they're done. The delay block will hold an agent at this block for a specified period of time, which can be a fixed time. Okay, hold this agent for 5 minutes. Whenever you get an agent, hold it for 5 minutes. Or it could be a random time. Okay, on average, you have to hold them for 5 minutes, but you could have a distribution around 5 minutes. So the delay block, although the name sounds like you're waiting, but it's not waiting. The delay block is used to model processing time. So let's say you have a process step which takes 5 minutes per unit. So you would put a delay block for 5 minutes, and that would delay the agent for 5 minutes. That represents that the agent is being processed for 5 minutes, and then the agent goes out the other end, and that step is done. The queue block is used to have queues, like waiting queues. So agents which are customers or products are waiting for the next step to be free or some resource to be free. They get queued up. It could also represent inventory. So you could have a queue which represents work in process inventory. So inventory waiting between different stages of the process. Okay. Then, because very often we have a queue, which is like a work in process inventory, followed by a delay, which is like a workstation or a process step. We often, in our process modeling, you'll have a queue and a delay, queue and a delay, when you're modeling real life process, because real life process, they often allow some work in process inventory. So you want to have a queue for that. So to just make your life easier, instead of having to drag two blocks into the simulation window, AnyLogic combined the queue and delay into this block called service. So service is basically just a queue and a delay block put into one block. So it's basically you took this block, connected this to a delay block, and then you drew a bigger rectangle around both of them and called it a service block. So that's what service block is. It's internally it's just a queue and a delay. Okay, and this can be used to model a workstation, which allows a pile of work in process inventory in front of it, or a process step in healthcare where some patients have a waiting area, they can wait in front of that process step. Anything like that you can model with this, or alternatively you can just put a queue and a delay. It's the same thing, or a service block. Resource pool models workers or machines that are going to work on the customer. So for example, you could have a resource pool called nurses, and let's say in your hospital unit that you're modeling, there's 10 nurses present at a certain time. So you can put the capacity of that to be 10, which means you have 10 of this resource. And then different process steps like these delay blocks, they can have a seize and release block, or the service block can do that too. They can seize a resource. So let's say a patient comes in, you need a nurse to see the patient. They will seize a nurse from the nurse pool, and then that nurse will not be available anymore until that patient leaves the block, and then the nurse will come back into the resource pool. So this is used to model limited resources. You can get statistics on the utilization, and it's very useful because this resource pool doesn't need to be tied to one block. This, let's say 10 nurses could be supporting multiple process steps. So there could be an intake step, there could be a step where you take the patient's vitals, there could be a step where you help the patient do something else like blood work. And so any of those blocks could draw on the nurse pool and pick up a resource of a nurse and then attach it to the agent, which is the patient, for a certain amount of time to do that process and then release the nurse back. Okay, so the good thing about resource pools is these could be shared resources across multiple steps. This is very useful. A lot of times in real life, you have space constraints. Okay, so let's say you're modeling a checkout place in a retail store. And the checkout place, there's only space for 30 people to stand in. There may be 2 or 3 checkout lines, and at most 10 people can stand in a line. So at most there could be 30 people in the checkout area. This is a pair of blocks. There's 2 blocks. You could have a restricted area start block, which is this one on the left, and then a restricted area end block. So you could put these outside the process, which you want to control the space for, and then you can limit how many people can be inside these brackets, these restricted area at a time. So it would count up all the people at different queues, at different delay stations inside these two brackets. It'll make sure the sum of all those people is less than equal to the maximum amount allowed for the restricted area. So if an area can only have 30 people, it will make sure that all the queues and all the processing steps, they add up to 30 agents only. And then the next agent will not be allowed to enter that area until somebody leaves, and then the next person can enter. Very useful to model, for example, a parking lot. Right, so if the parking lot is full, these parking lots, they have gates that can close, so the parking lot will not allow a new car to enter if all the spots are full. And then if some car leaves, then a new car can enter the parking lot. So you could do that with these blocks. And then we have a pair of blocks called time measure start and end. You can put them anywhere in a process. They're linked. So the time measure end block on the right, you have to tell it which time measure start block to link to. And then any agent that goes past the time measure start, they have a timer that started on that agent, and when it reaches time measure end, you stop the timer for the agent and you figure out how long did this agent spend between the start and the end of points. So let's say you want to measure throughput time. How long does a customer spend in your process? You put a time measure start block at the beginning, right after the source block, and then you put a time measure end at the end just before the sync block, and that'll measure the time the agents spend in your process, which is the throughput time, how long a customer spends in your process. Okay, so let's build an actual simulation model, and you'll see how easy it is and how cool it is. So in the first example, we're going to test the theory we learned about bottlenecks. So this is like a very simple step A, B, C, D process that you might have seen in the process analysis lecture. So the cycle time of each step is given. So step A takes 10 minutes per unit, step B takes 12 minutes per unit, step C takes 15 minutes per unit, step D takes 10 minutes per unit. Now we know from our previous lessons that step C is the bottleneck. And so we said that the capacity of the whole process is just the capacity of the bottleneck. So what's the capacity here in units per hour? We take 60 minutes divided by 15 minute cycle time. That gives us 4 units per hour. So what we're saying is this whole process, even though other steps are faster, will give us an output of about 4 units per hour. Okay. So we can model this process in AnyLogic. We're going to have a source block to inject people into the system. Okay, and we want to set the demand rate to be higher than the bottleneck capacity, which is 4. If the bottleneck capacity was, let's say 4, let's say it is 4, and let's say our demand was 2 units per hour. So 2 agents enter per hour. You're going to output 2 agents per hour because you're not hitting the bottleneck. The bottleneck is not a constraint right now because your demand is so low. Only when your demand exceeds the bottleneck capacity will you see the bottleneck become a constraint. So just to test if really our process can only work at the speed of the bottleneck, let's set a higher level of demand, 10 units per hour, and see can we get more than 4 units per hour out of the system, or are we really limited by the bottleneck? Let's check our theory, right? So we can, each step here becomes a delay block. So see these delay blocks, we just drag them into our model. And for each delay block, there's a delay time parameter, a property, which we set to 10 minutes for step A, 12 minutes for step B, 15 minutes for step C, 10 minutes for step D. Okay. Now, if you ignore this queue, you just connect the source to step A and then the sink to step D, then that would one-on-one match this process diagram we had here, right? So the model in AnyLogic is very closely matching the process diagram we had. The only thing is that each rectangle in a process diagram became a delay block, and you had to add the source and sink blocks at the end. Okay. So why do we need to put a queue here? And actually we have to make the queue have like maximum capacity, which is like infinite capacity. Well, the reason is the source block, when it generates an agent, it can't hold on to that agent. It has to push that agent into your process. Now, if step A is already working on the previous agent, the previous customer, step A cannot accept the next agent. So the AnyLogic will throw an error, say, well, the source block cannot be blocked. Remember blocking and starvation? A step or process step is blocked if the next step is not ready for its work. So I am done with my work, but the next work session is not ready for my work, so I can't push my work over. So I'm blocked. I can't do anything. I just have to wait. I'm going to wait. When the next block gets done with their work, I'll pass on my thing to them, and I'll start working on a new thing, right? So all these delay blocks can get blocked. They have the logic built in. So if step A is done, but step B is still busy, step A will be blocked until step B becomes free again. Then step A will pass on the agent to step B and take a new agent. So all these delay blocks are fine, but the source block is a special block which cannot be blocked. The reason being, if we block the source block, it will look like our demand fell, because our demand would then become a function of our process capacity, which is, we don't want that. We want to capture all the demand, and then some of the demand we may not be able to process, right? Just be extra demand. Our capacity is too low. We can't handle all the demand. So that demand will just get saved in this queue. And at the end, we'll see, okay, we got a demand of, let's say, 1,000 units. We only processed, 400 of those units, and 600 units are still in this queue, which were demand we could not process because our capacity was too low. So we can see what portion of the demand we were able to process. So we have to put a queue here because the source block cannot be blocked. It has to push the demand out, and that is for a good reason, because you want to capture all the demand in a queue here to see how much demand there was. Otherwise, you'll see, oh, the demand was low, maybe that's why my output is low. Well, no, if you put the queue will show you your demand was high, your output is low because of the bottleneck, right? So let's make this process in AnyLogic. So I kind of made this process already, but I'm going to make a new model to show you how to do it. So let's make a new model, okay? And I'm just going to call it test model, okay? And this is useful. I'm going to set the model time to be hours, okay? It doesn't really matter because you can always convert between units, but I'm going to work, my capacity, I'm thinking of it in per hour, right? My bottleneck is step C, which is 4 units per hour. So you can set the units you want to think about, and you hit finish, and you get this new model, okay? And you can see in projects, I have multiple models open, but you can close these, like you can close this, and so they'll close one of the windows. So you can, in your projects, you can click on whichever project you want to work on. You can double click that, it'll go to that project, right? So whichever project you want to work on, you can switch. You can have multiple projects open at the same time. I don't recommend you have too many projects open because, your computer, depending on how powerful it is, it may get things to make it a little bit slow. Anyway, so let's see. So the first thing I do when I start with a blank model is I change the zoom level to like 200%, because otherwise things are too small. Maybe I'm getting too old, but things tend to be too small for me at the default zoom level of 100%. You see the icons are pretty small, depending on the screen resolution, because this software is built in Java, and it's a bit, but anyway, so the user interface is a little bit dated, and it doesn't scale that nicely in terms of size for high resolution monitors. And so sometimes you see these icons that look a little bit small, but we have to live with that, I guess. Anyway, so let me show you this slide. So I'm going to put a source block, a queue, 4 delay blocks, and a sink. Okay, so if you start out here, this is your favorites. So when you really, let's say you use your delay block a lot, you can right click it and you can add to favorite, and then all your favorite blocks will be here. It'll be easy to find the blocks you want to use. Otherwise, the blocks we're going to use today are going to be in the process modeling library right here. And so what you could do is you could put a source, just drag it. Then I want a queue. When I drag it close to it, it automatically connects them. See how nice it is? Then I want 4 delay blocks. You just drag and leave. Drag and leave, and it just connects it automatically. Now I'm going to show you what happens if it doesn't. Let's say you put it somewhere here, it doesn't connect automatically, and then later you move it up. Well, it did connect automatically, but let's say, this was not here. How do you connect manually? You double click this green block, you go here, and then because you're ending here, you double click here, and it builds that connection. Always double click on a green circle, go to the next green circle, double click, and that can build the connection too. Okay, I have 4 process steps, so I need 4 delay blocks, and then I need a sync block. Okay, so I'm going to name these delay blocks something useful. So this is going to be like step A. Okay, so I can understand them. Delay 1 is not that useful a label. Step B. Okay, and this is my step C. And then I have a step D. Now, if you remember, or if you don't remember, you can just check the slide. Step A is 10-minute cycle time, then 12, then 15, then 10. So 10, 12, 15, 10. So let's go and set those times up. So step A is 10 minutes. So it says delay time, and delete whatever stuff in there. Just type 10. Make sure you pick minutes, because seconds will be really fast. So 10 minutes. Fast in terms of the demand rate, because demand is coming like 10, 12, 15, whatever units per hour. So if you have 10 seconds, they'll be like, you'll see everything will just pass through quickly. So make sure you make it minutes, because that's what we have in our slide. And then it is 12 minutes. And then step C is 15 minutes. And step D is again 10 minutes. Now make sure you leave the capacity to 1 for all the delay blocks if you have 1 worker. Later on we'll look at the case of, okay, let's add a worker to step C, see if the capacity goes up, and then you can change the capacity. That will kind of be like, okay, how many agents can be in this station, workstation or step at the same time? If 2 agents can be processed at the same time, that means like you have like 2 workers or something like that, then you can make the capacity 2, okay? But right now everything should be 1. Okay, Q, we want to look at maximum capacity, because this queue is not really a queue. We're just capturing demand we couldn't process, because source is going to just push out demand onto our process, and any demand which our process can't handle, we want to be just, to live here in the queue, so we can see how much demand we didn't process. We just set it to maximum capacity so we can capture all the demand that we don't process. In the source, now remember step C has a cycle time of 15 minutes, which means the capacity is 4 customers per hour. Step A's capacity is 6 customers per hour. So let's set the demand very high, see what's the maximum we can push out. So let's set the demand to 10 units per hour. Okay, that way if at the sync side we get less than 10 units per hour, then we know that the bottleneck or these steps slowed us down. If the demand was low, if I set to like 2 units per hour and I'll get 2 units per hour out, then I wouldn't know either the demand just low or it's my capacity, my bottleneck's acting up, right? My bottleneck's being a constraint. So I'm going to set the demand higher than any of the capacities of steps A, B, C, and D, just to see what is the maximum stuff I can push through this process, and to see if really does the bottleneck really limit my process and make me only produce at 4 units per hour. To keep the math simple, I'm going to go to projects. I'm going to click under my model name, my test model. I'm going to click simulation main. And here I'm going to say, don't stop, never. Stop at specified time and stop after 100 hours. Remember we set the model units when you made a new model into hours. So it's going to, that's the hours. This is going to be hours. Stop at 100 hours. Then also I'm going to do fixed seed of 42. So I'm going to be using a seed of 42. The seed chooses the random values, which is your demand is going to be random arrivals, right? So if your seed is different than my seed, then you'll get slightly different demand and your results could be slightly different. But if your seed is the same as the seed I have, which is 42, then you should get the exact same results if your settings are exactly the same as mine. So the seed is chosen so that different people building the same model can match their results and see whether they got the same results or not. Okay, so we put the seed to 42. We said stop after 10 hours. So if 10 people arrive per hour, after 100 hours, we should get 1,000 people arriving. Okay, so if our bottleneck capacity is 4 units per hour, after 100 hours, we should have 400 people out here. Okay, because our bottleneck would be limiting our capacity. If it's not true that the bottleneck limits our capacity and step A can do 6 units per hour, we might get 600 out here, right? Let's test our theory. Or if nothing here is limiting factor, then all 1,000 that arrive, 10 per hour for 100 hours is 1,000, should end up at the sink. Okay, so everything looks good. Let's run the simulation. You go to this green button, you press run the model. Okay, and a new window will open up, pop up, and you'll see customers arriving, customers going through the system. You'll see these different steps. See, the step A and B always have something in them because they're getting blocked by the next step, and so when they're blocked, they can't really they don't go to zero because they have to keep the agent until they're being blocked. And once they send the agent to the next step, they pick up the next agent. Whereas step C is being stopped, so it's zero for a time, right? When it sends out something, it doesn't receive the next agent at the same time because step C is the bottleneck. So step D is having starvation, which is why it's going to zero, it's having idle time. And step A and B are being blocked by the bottleneck. So steps before the bottleneck get blocked, steps after the bottleneck get starved, and this is the bottleneck, right? Now you can increase the speed by clicking this plus button to speed up the simulation, or you can just press the double arrow just to go to the end, which is the 100 hours we set, similar to 100 hours. And so after 100 hours, we can see that the demand that was generated was 1,089 customers or units or whatever to our process, right? Which is, because that demand is random, it's not exactly 1,000. So on average, 10 per hour times 100 hours should give you about 1,000 on average. And so because it's random, it's a little bit above or below, right? 1,089. 688 were still in the queue. 401 went to step A. 400 went outside that. 400 went to step B. 399 went outside that. All the way at the sink, the ones which we finished were 397. So 397 units were done in 100 hours. So if you take the average, 397 divided by 100, 3.97 units per hour was our effective capacity in this simulation, right? That's how much we could process. And you might say, well, T said it's supposed to be 4. Why didn't we get 4? I'm going to explain that next. And this will often happen with simulation because there's a ramp up period. The first customer to arrive doesn't arrive when you start the simulation at time 0, then there's no customer in the system. Because it's random arrivals, the first customer may arrive after 20 minutes, or may arrive after 30 minutes, or may arrive after 5 minutes. So there's some time in the first hour that is lost because no customer is there. So when the first customer arrives, you've already lost some time. So now you don't have a full 100 hours, you have less than 100 hours, right? Then, because step C is the bottleneck, the first customer takes a good some time to get to step C because step A takes 10 minutes, step B takes 12 minutes. So after 22 minutes of arrival, does the first customer get to step C, which is the bottleneck. And step C is the limiting factor. And you can see only 399 customers got to step C, and it processed 398. Now, again, after step C, because step C gets the first customer quite a little bit after the simulation starts, you've already lost some time out of the 100 hours. Then you also have to factor in that when we say the process capacity is 4 units per hour, that's like the long run average. If you only run it for 100 hours, what you get is that some units are going to be in step D, which are not counted at the end. So there's a 1 unit in step D, which has been processed by step C. So this should have been 398, but it's not because step D is still running when we stop the simulation. Okay, so because the first customer arrives to the bottleneck late, not at time 0, like after time 0, so you lose some time there. And then this, after the bottleneck, there's some other steps which are gonna have some of the outputs in them. When you stop the simulation, you're not gonna get exactly 4 customers per hour from your simulation, but if you run it for longer and longer time, your average will creep up to 4. So if you run for, let's say, 1,000 hours, you get like 3.99 customers per hour. So the simulation in the long run gives you values which are going to approach the mathematically pure calculation. Okay, why do they approach the mathematically pure calculation and not actually reach it? Because of the issues I mentioned. The system starts in an empty state. There's a ramp up period where the first customer has to arrive, get to the bottleneck. This whole ramp up period is not being constrained by the bottleneck. So it's not, its time is being wasted from those 100 hours which you're merging the simulation over. And so because of these reasons, you're going to approach the theoretical value of 4 with your long run simulation. And so that is what you're going to get. Okay, so that's what I explained here. The simulation shows 397 because the first arrival is not at time 0, and step C can process 400 items in 100 hours, but it would take slightly longer than 100 hours for the 400 item to leave the process after leaving step C. So because we don't give the 400th item enough time to get to step C and then leave step D, we end up with a little bit less than 400 items, because 400 over 100 hours would be 4 units per hour. However, we do see that the whole process runs at the speed of the bottleneck. The output of none of the steps is more than 400. Okay, step A's output is 400, step B's output is 399. Nobody could do more than 400 customers per hour because of blocking and starvation, like we mentioned in the previous lecture. So the bottleneck determines the pace of the whole process. If the bottleneck is 4 units per hour, the whole process is going to run at 4 units per hour speed. And if you have extra demand, that's just going to be, you know, either they wait here or they just walk away, but you lose that demand. Anyway, this was the extra demand, 688, that the system did not handle. Okay, so as you saw, with a very simple any-logic model, we could simulate this process and we could verify that indeed the bottleneck is step C, and the capacity of step C is limiting the capacity of the entire process. So the process capacity is the bottleneck capacity. Now, let's measure the throughput time, okay, which is the time an agent spends in our system. So to do that, we go to the process modeling library, and we want to use those time measure start and end blocks. So I'm going to put time measure start just before step A. I'm just going to call it TS for time start. Okay. And it moved the label to the left. I'm going to drag the label to the center here. So TS for time start. Okay. Well, why am I not starting time in the queue? The queue is just here to capture the demand I can't process. The queue is not really capturing waiting time in the system. Now, if you did have a waiting area before step A, then you would have I would add a second queue here with the capacity, which would be the capacity of the waiting area, and then the time start would be before the second queue, because the second queue would be the actual waiting area time. The first queue is just to capture the excess demand, so I know how much demand I didn't process. Okay. So if there was a waiting area before step A, you would add another queue between time start and step A. And then you set the capacity to the capacity of the waiting area. This queue has unlimited capacity. It's just you can call a mathematical box to capture demand you can't process. So you put time start, then you drag time measure end block at the end just before the sync block, and I'm just going to call it TE instead of time measure end, that long name. Okay, that's my TE, time end. And because you can have multiple time starts blocks, you need to tell TE which is the start timer. So here, time measure start block, you press plus and you choose TS. And now these two blocks are linked. TS will start the timer, TE will stop the timer for every agent and give you the throughput time. Now, theoretically, we know what to expect. We know that all these process steps are running at the same speed as the bottleneck, which is step C, because of blocking and starvation. So step C's pace is going to control the pace. So step C's pace is what? 15 minutes per unit. So this is going to run at 15 minutes per unit, 15 minutes, 15 minutes, 15 minutes. It should take 1 hour or 60 minutes throughput time for my units to get through, because that's the pace at which the process will run. Okay, so whenever you have a time end block, okay, it saves the timing data in a variable, and you can see that variable by going to the analysis area, and you can just drag a histogram here, Okay, and in this histogram, we're going to put the title as it's going to be our throughput time. Okay, and then under data, under histogram, here you'll say TE, which is the time end block's name. Whatever name you put here, if you put time measure end, or you called it John or Paul or Bobby or my best friend, whatever you called it, you have to type the name here under histogram, under data, type dot to access the data inside time end, and type distribution. That's going to get you all the time distribution data to plot on this histogram from the time end block. Okay. And so if you go to the histogram, TE, the distribution, because this is called TE. Now let's run the simulation. And you'll notice that the first few units went through the system in less than an hour. Why? Because step A and step B are not being blocked until the third unit has entered the system. So the first two units go faster to step A and step B than 15 minutes per step, and then from step C onwards they start getting 15 minutes per step. But by the time the third unit comes, blocking is already happening because step C is working on the first unit, and then everything else after the first 2 or 3 units is going to take 1 hour. So you can see this is the time in hours, and you can see that 1 hour, every unit is taking 1 hour to go through the system. Only the first couple of systems, because as I mentioned, there's a ramp up time when your model is not giving you the steady state results because everything was empty. Like you open the shop, everything is empty, there's no queues. So the ramp up period, you have to ignore those data points. And in the ramp up period, we did get throughput time below 1 hour, but now everything is 1 hour. Okay. So 0.9 to 1, actually every value is 1, but because the histogram has buckets, all values are falling between 0.9 and 1 hour. Every value is actually 1 hour. So it's taking 1 hour for every single unit to pass through. You can increase the speed to get done faster, or you can just go to the end. And you can see again, we got about, the same, because our seed is the same, 42. The random arrivals are going to look the same each time we run the simulation, unless you change the seed. And so we again got the same output. And everybody, the throughput time is 1 hour, as we expected. So the theory is working as expected, which is a good sign, because when you build the simulation, you first want to start with smaller models where you test where the output matches what you expect, and then you make the model more complex. Okay, so that worked out really well. So the throughput time matched what we did. Okay. So I'm showing you the same. I just showed you these results in logic. This is just showing you the same results. Now let's increase the capacity. So let's go to this example, which we have seen in a previous lesson before, or if you've not seen, that's fine. So again, we have 4 tasks, 2 minutes per unit, 4 minutes per unit, 5 minutes per unit, 3 minutes per unit. Obviously, task C is the bottleneck with a capacity of 60/5 or 12 units per hour. Okay, but what happens if we add an additional worker here, double the capacity of C, then this becomes the bottleneck, and the new capacity should be 15 units per hour instead of 12 units. So before we added a worker, our bottleneck was stuck at 12 units per hour, and after we added the worker, task B should become the bottleneck, and our capacity should go up from 12 to 15 units per hour. So let's test that. Okay. So let's go back to AnyLogic. Okay, what I'm going to do is I'm going to change all of this to, this is going to be 2 minutes per unit, right? What was in my slide? So 2453, 2453. This will be 4, and then 5, and then 3. Okay, so that's my base process. I'm going to make sure that the source demand is set to a higher rate than my capacity. My capacity right now is 12 units because of the 5-minute bottleneck cycle time, 12 units per hour. So I need the demand to be higher. I mean, it's going to set to like 22, something crazy high. So my demand is not the limiting factor. I can actually test the bottleneck in my process. Right? Any extra demand will just be captured by this queue. So don't worry, the queue will capture the demand. So let's see what we get. So if our capacity is 12 units per hour, after 100 hours, we should get close to 1200 units out at the sink, right? So let's run this. Okay, let's go to the end, and 1198, very close to 1200 units, we got out at the sink. Okay, so that's working. Now, how do we add a worker at step C? Because remember we said in our slide, if we add a worker at step C, phi would no longer be the bottleneck, because its effective cycle time will be 2.5 minutes per unit, because it'll do every 5 minutes, it'll output 2 agents, 2 units. And so this will be the bottleneck, and this has a capacity of 15. So if I increase the capacity of task C from 1 to 2, I should be able to get about 1500 unit output, which corresponds to 15 units per hour, because I'm running for 100 hours. Okay, so let's do that. So I go to step C, the capacity, I increase it to 2. What that means is this can take in 2 units at the same time, and the 2 units will wait for 5 minutes and then go at the same time. So it's going to handle twice the number of units it was handling before, which means it's no longer the bottleneck. This is the bottleneck. My demand is still high enough, so I should be able to see the effect of the bottleneck, and I should be able to get close to 1500 units here instead of 1200. So let's run. Okay, and you can see 1497. I almost got 1500 units out when I increase the capacity of step C to 2. Okay, let's actually run the simulation again without speeding it up, and notice step 2 sometimes goes to 2. See, 2, 2, 0, 1, 2, 2. It goes, keep going back to 2. It's keep taking in 2 agents to process them at the same time. Because of the 2 workers, we increase the capacity here. So that's why this is the bottleneck, and now my effective capacity is 15 units per hour. Okay, which is why after 100 hours, I get about 1500 units output. And I hope you enjoyed using AnyLogic, and I hope you learned how to do some simple, at least, simulations of processes. And these are really useful tools to be able to see how you could change the demand around, see what happens when demand falls, demand goes up, what happens if you add some work in process inventory at different stages. You could do all those what if scenarios and see how your system behaves using these simulations.